This is video 41 in the lectures on the design of reinforced concrete beams. This lecture deals with pre-stressed concrete and more about the pre-stressing reinforcement. We start first with the wires. Wires in a typical stress-strain diagram with some numbers to it. For a wire, we have modulus of elasticity of 200,000. We have the characteristic tensile strength typical of 1,800 megapascal. Then we have the characteristic or the 0.1% characteristic proof stress FP01K. The proportion of FPK divided by FP01K should be larger than 1.1. There should be a difference of at least 1%, 10%. And a typical value of epsilon UK is 40 to 60 micron as epsilon U. So epsilon UK is the characteristic value of the ultimate strain, of course. The wires typical diameters range from 4 to 12 millimeters. The design diagram is then the stress and the strain, and it's a bilinear diagram. It's just the value FP01K divided by gamma S, which is 1.15. But we will use always the horizontal branch and the linear branch like that. Epsilon UD, the maximum strain is 0.8 epsilon UK, the ultimate strain, and epsilon UK for high bond is 35 per mil, and for plane surfaces is 20 per mil. The modulus of elasticity of the pre-stressing reinforcement EP is for strands 195 gigapascal. Just take care, this is a mean value because there is a range depending on the system. But for wires and bars, we take 205 gigapascal as a convention. Then we have strands. The strands are composed of different wires and then coated. When you combine the different strands into one element, then we talk about tendons. So this is one tendon with 7 strands, for instance, and each strand has an amount of wires. The tendons are then bundled together with a system where you can put stress on each strand separately. You can also have single bars as pre-stressing reinforcement. It is sometimes used for retaining walls. It's a high tensile yielding material, like for instance Dividax, and with large diameters. They were used to make anchors with an anchoring system. In a pre-stressing environment, you can have with pre-tensions, everybody understands that each cross-section has an applied force due to the pre-stress, because first the strands are put under stress and then afterwards the concrete is poured on top of it. And so each section has an applied force. But it's not so clear what happens with post-tensioning when the tendon is not adhesive, because you have ducts going into the concrete where you put in later on when the concrete has hardened cables in it. So it's non-adhesive. So how does that work? Well, in fact, it's you can simply indicate it by saying that this is the tendon. You have pulled on it with a force F, then you blocked it, so there is an external force coming onto the concrete, which is F, following this line. It means also that because you have pulled on this cable, that you have an upwards force alongside the cable pushing against the concrete. So if you now, when you now make one cross section here, doesn't matter where, and you look at the equilibrium of the forces on the right, and you make it in an equilibrium on the forces to the left, then you will see that the internal forces are in fact equal to the forces of the pre-stress. So it means that we act as if the pre-stress is present in each section, because there is an equilibrium in each section. It is not so that the pre-stress is only there at the beginning of the beam and at the end of the beam. No, it's present in every section because of that equilibrium that you need in each section. So in fact, there is no big difference, mechanically speaking, about those two elements. So the pre-stressing force is then like a load of bending moment, normal force, and shear force in the cross section. We handle pre-stress as eccentric bending under a normal force and bending moment. The normal force can be an external load plus the pre-stress, of course. And the bending moment can be the external load coming from permanent or mobile loads plus an eccentricity of the tendon. So the pre-stress is there in the normal force and in the bending moment. Suppose that you have a cross section with the reinforcement marked by P and the cross section AP. Then we look at the stresses on top of the beam and stresses on bottom of the section. We have to calculate the maximum and the minimum, because the maximum, that's clear. You should not have a system that the concrete is breaking, of not resisting the compressive force. The minimum, because you do not want tensile stresses, or you want a limited tensile stress. So you have a concrete stress minimum, maximum, top and bottom, and you have to do calculation in SLS and again in ULS. So this whole process is an iterative calculation to see what the stresses are. You learned now something about the pre-stressing reinforcement, and next lecture we will look at how you can do it.